we finally got to the fourth and last method of calculating wind loads, the main wind force resisting system for a building. I was very surprised to see the results and how they compare between this method and the other three methods that we calculated so far. If you stick to the end, I also have a special announcement to share. Let's go. Alright, as you've seen before, this diagram here shows all the wind load related chapters in ASC 716. For the main wind force resisting system, we have 4 procedures for buildings. We have directional procedure part 1 and then part 2, and the envelope procedure part 1 and then part 2. We have covered already 3 of these procedures, all the envelope procedures and also the directional procedure part 2. Now we're jumping into part 1, which is also considered the all heights method. The first thing I want to point out, as usual, are the limitations. This method is very lenient. It's the most lenient method in the sense that we can use it for a wide variety of buildings. The limitations that we have here are essentially the same limitations that we also have for all the other methods. And this is a paragraph from ASC 7. It shows here the conditions and the limitations. The main ones that I want to point out is the building needs to be regular shaped as defined in section 26.2, and it cannot have response characteristics that make it subjected to a crosswind loading, vortex shedding, and all these other items that it's mentioned here. It's a little bit confusing to understand what these things actually mean, and you see here that if you have these response characteristics, you have to either account for these loads using recognized literature, and there is some language in the commentary and I think some equations that you can potentially use, or you can do a wind tunnel procedure, in which case they simulate the actual building and they essentially do a wind tunnel test. You can look it up. It's pretty sleek. It also costs money, but the taller your building is, the more flexible it becomes, the more the shape of the building may cause some of these response characteristics. And also, if you use the codified procedure, you probably will get higher pressures, and therefore it would be more economical to pay for the wind tunnel test as opposed to just following the procedure from ASC 7. I'll go over at least one of these items here on the conditions for this method, essentially vortex shedding and a crosswind loading. Or crosswind movement. What this is essentially is when you have your wind load going in this direction, you may have some vortex shedding or vortex being developed on the other side, especially if your building is round. And what this causes essentially causes some sort of load perpendicular to the wind direction, or maybe in the other direction here. And you can see here that this would cause movement in the direction that's not the direction of the wind, and that can cause some sort of instability. And it really is dependent on the shape. You can see here if your building is a triangular shape, that it's also subjected to that. If it's rectangular shaped, it is subjected to that, but maybe not as much as if it's round. And then obviously if you allow movement from the inside of the building, the interior of the building, which that would be very unusual, you have a better behavior for that vortex shedding because you don't get that response as much, or the vortexes are not generated as much. I hope that clarifies this a little bit. You can do some more research on all these different methods and let me know what you find out, but these things are more predominant the taller your building is and the more flexible it is, but always looking at the shape of the building, because the shape may also impact how these different responses will occur. Now for our steps, again, you can go through all these steps in this table 27.2-1 from ASC. We're going to do our example here, the same example that we've done before, and I'm going to outline all these steps that we're going to follow in the directional procedure part 1. The first step will be calculating the velocity pressure, QZ or QH if it's at the top of the building. And then we're going to determine the wall pressures, determine the roof pressures, calculate the total base shear and the total uplift. At the end, we're going to compare this method with all the other 3 different methods that we have already calculated. Step 1, let's calculate the velocity pressure, QZ and QH. We are going to use this formula here with all these different wind parameters that were given in the problem statement. There is this table here in chapter 26 where you can calculate your KZ, and this factor is really to account for the pressure on the windward side of the building. We're gonna see that here in a little bit, but what I want to point out with this table is that this is dependent on the height. In other words, the higher you are in your building, the higher this coefficient is, essentially stating that the pressures will increase as you go up the height of your building. If we are in exposure category C, so these would be the coefficients that we would be using. So if I put all of this on a table, we're gonna see that for 15 feet, we have KZ of 0.85. If I apply that equation up above, I get 53 as my pressure at the base of the building, 15 feet. And then if I go to 20 feet, it increases to 57. And then now I name that QH because 25 feet is the total height of my building, and my pressure there is 59 psf. This is not the wall pressure, this is the velocity pressure. We're gonna get to the wall pressures now using a different formula. Step 2, like I said, is for calculating the wall pressures. This is the formula that I was mentioning, and you can find that in chapter 27. This formula is both for the walls and for the roof. You're gonna see this, and what's gonna change here will be the C sub P values, or your external pressure coefficients. There is another term here that we didn't have before. One is the gust effect factor, G, which is this guy right here. And then we also have GCPI, which is this other guy there. And what this is essentially the gust effect factor is either 0.85, or you can take a different value. It's based on the rigidity of your building or how flexible your building is. You can look up the definition of that. I'll keep it short here so that we can get through the example. But the other one I wanted to mention is GCPI, and that is the internal pressure coefficient. This one I do want to spend a little bit more time on, and I want to show you here this diagram. And the pressures are the arrows inside the building. Those are the arrows indicating the direction of the wind inside the building, the internal pressure. In our case, we have an enclosed building, so this diagram is very appropriate. But you can see here that those arrows cancel out. Per ASC 7, if your wind is going towards the surface, that's positive wind load. If it's going away from the surface, that's negative wind load. So this would be a positive internal pressure. But you can see that these two pressures here, this one and this one, they cancel out. So as we are going through wall pressures, it doesn't really matter, the internal pressure. And this portion of the equation will get canceled out because these two guys are equal and opposite. And the same thing here, when you have negative internal pressure, they also cancel out. It's not going to be the same for the roof. You can see here that there's no internal pressure, going down to the ground here, because we're just looking at the roof surface. Then it actually either adds or subtracts from the roof surface. But let's stick with walls for now. And now let's look at this other table from ASC 7. And here we have essentially all the C sub P coefficients. And the table tells us for a windward wall, we're gonna use these coefficients all with QZ. And this is telling us that the pressure here is gonna be increased, and pardon my chicken scratch here, but it's going to increase with the height. Whereas if you go to the leeward wall, which I wish they put lines here to divide these guys, but it's all these numbers here. The table tells us to use that with QH. And that's telling us that the pressure here is going to be uniform. So this diagram here is not really appropriate because it should be that gradient per se on the windward side, and then the leeward side is a constant pressure because that's based on QH. So just to recap, this is our building, and I want to introduce here a concept that we've covered before, but I'm going to call it wind A and wind B. And just to recap, wind A is towards the wind is parallel to the short direction of the building, and then wind B, the wind is parallel to the long direction of the building. And I want to clarify that here so that we can see on the table how this is all organized and how I separated here my coefficient L over B, that's 0.75. So based on that, I know what my windward coefficient should be. That's 0.8 because that's for all values of L over B. And then for my leeward side, I know that I'm right here in this negative 0.5, and that's what I got here on my table. And then the sidewalls, not as important for us if you're calculating base shear in our case, but I have the value there. And then here on this height, this would be the height at which the pressure would be applied. So windward, we'd have two separate pressures or three separate pressures because that's associated with QZ, whereas leeward and the sidewalls would all be associated with QH, so just one pressure. If I do the same thing for load case B, I got my coefficient here, 1.33, and then all my pressures are calculated in a similar manner. What I also wanted to point out here, and I'm not going to do a whole different check, I'm just noting here that all these pressures are greater than 16 psf, which is the minimum wall pressure per ASE for all the methods. Now, it's not like if one of these pressures was less than 16 psf, we'd put it at 16 psf. The way that the code is worded is really that you need to have a separate load combination, that all the wall pressures are 16 psf. And I think the projected area for the roof, so you're really worried about overturning when you're checking the minimum requirements. The projected pressure for the roof, so in this case here, this pressure here would be 16 psf, and then let me delete this down here, and then, or this would be 8 psf for the roof. Let me try to write better here. This would be 8 psf, and then you would have 16 psf down here, 16 psf. That would be to check the minimum. By inspection, we know that this would not control, because one, our roof is flat, so we don't have the 8 psf component, and two, all of our wall pressures are greater than 16 psf, so we don't even need to run that load combination. Some companies may have their spreadsheet set up so that if any of these pressures become less than 16 psf, you just put them as 16 psf. This way it's slightly conservative because you're not running a separate load combination, but I think in most cases you wouldn't find that as 16 psf, maybe in low wind speed areas. Now, step number 3 is determining the roof pressures, and this step is very similar to calculating wall pressures in the sense that we're going to have a C sub P coefficient, but we have a little bit more cases to compare. It's similar because we're going to be using the same equation as you see here. The difference is that we're not canceling internal pressure, as I mentioned before, and then we have this table that guides us based on a coefficient H over L, as you see here, and our roof is a flat roof. So essentially we have different tables or different lines or rows on this table for different configurations of roof and different slopes. This is where we land. And you can also see here where these would get applied, and then this guy's here as well. So let's see for our load combinations. We have a factor of H over L equals 0.28 for load case A and 0.21 for load case B. So because they're both less than 0.5 and we would be falling in this category here, we're all going to use the same C sub P coefficients for both load cases. When we organize this and put it in a nice table format to understand all that's going on here, we have this. Now, let me explain why we have 4 different pressures here. You see here 4 different columns, right? Case 1 plus, case 2 plus, case 1 minus, and case 2 minus. Just the way I named these cases. We have this because this table gives us 2 values for C sub P. So, and we have internal pressure that can be either positive or negative. If the internal pressure is positive, the coefficients GCPI is positive 0.18. If it's negative, it's negative 0.18. And then for each one of them, we're going to run a case in which C sub P is negative 0.9 and then C sub P is negative 0.18, and do the same thing for the internal pressure. Then we come up with all these different pressures here, and I'm highlighting again even, the pressures that would be controlling for uplift, which is what we're concerned with. But I want to also point out that we have this other case, case 2 minus, when you have your internal pressure being negative. In other words, if we have our building here and the pressure is going down, the negative internal pressure, my coefficient for my C sub P is very low. It's actually 0.18 because one side of the equation gets multiplied by 0.85. If you do the math there, what you're going to end up is with a low vertical pressure. And this, when you add these two together or you subtract them, the net pressure is actually going to be a positive number because this internal pressure is higher. That's why you're going to find this 2 psf or approximately 2 psf downwards. And this is important, especially for load combinations in which you combine dead, live, and wind. You have the wind is actually adding on to dead and live load. And you should also be checking this if you have a long truss, for example, on the roof, to make sure that you're also accounting for this load combination. Obviously, if you are using main wind force resisting system, and if you're not using components and cladding to design whatever element you're designing. I hope this was clear. Now, this is going to be applicable for both load case A and for load case B. Now, we're going to calculate the base shear and the uplift in step number 4. To do this, I just want to reiterate what I had said before, which is how we're going to be applying this load. We see here what I had mentioned, that this load is constant. You can see that here it doesn't go to 0, it actually caps out at a certain pressure here, and that's because it's at 15 feet from the ground. And then on the other side, this is constant. You see 2 arrows here for the roof because it can either be positive or negative, as we discussed. And this is a plan view also showing the sidewall pressures, which won't really play a factor here in our case. So if I organize my pressures and calculate the base shear, I have for load case A a windward pressure of this much, and then while A and B, and I calculated my leeward pressure, I added, one is positive and one is negative because one is going towards the surface, the windward surface, the other one is going away from the leeward surface. But the absolute value of the two would be my base shear down here, so you'd be adding them up. And these are the numbers that I get for my base shear. If I go to my roof pressures, the coefficients were all the same, but where we're going to apply the roof pressures will be different, because one case I have load case A, the other case I have load case B. So I get here the zones with the different coefficients that I'll be applying my roof pressure to. And then I calculate my total uplift here on each load case. I'll make this a little bit simpler, and I'm going to bring up a diagram for wind A and wind B. That's just a little key plan there for us to know which one is which. You can see here for load case A, if I plug and chug all my pressures, and I actually tried to draw this somewhat to scale, at least with the building dimension, and you can see if you were to design this building, you're building a model and wanted to squeeze in all the pressures and really try to hone into what you should do for your load combinations, this is what you should do. If you're trying to capture the most uplift on your building and also the most overturning force on your building, you'd be looking at this diagram. And then for load case B, you can see, because load case B is parallel to the long side of the building, that this 26 psf is stretched all the way to the end, but everything else remains the same. There is one thing that's different on the leeward side, that for load case B I have a little bit less pressure on the leeward side, whereas load case A we have a bit more. Now, how this method compares with the other methods that we've seen so far, this is a table showing all the different methods that we've done so far. If I calculate a percentage in comparison with the envelope procedure part 1 comparing to the directional procedure part 1, I'm going to put it in a graph here so that it's easier for us to see what happened. So For base shear in both conditions, I went from 479 to 398 for load case A. And this, not for base shear, sorry, for uplift, this really decreased my uplift by 17%. And then for load case B, I decreased my uplift 23%, which this was a little bit surprising to me because I thought that the uplift was actually going to increase because the base shear increased, as we're going to see here, that in envelope part 1, I had only 132 of base shear, it increased 75%. So in other words, if you can use the envelope procedure, and if your building is like a moment frame, for example, a pre-engineered metal building, they use this method all the time to really squeeze in and the capacity and make it the most economical building possible. You probably want to be using the envelope procedure because the directional procedure is going to give you 75%. It may be different depending on your wind speed, your building geometry, but it's a very high increase in base shear. And we see here on load case B that this increased to 165 kips, and that's a 72% increase. So it is worth it to know all the different methods. My opinion is that ASCE 7, they need to get rid of at least these other two simplified methods like envelope part 2 and the directional procedure part 2, because let's be honest, who is using the most simplified methods? I don't know. If you know people who use those, great, let me know in the comments below. But I haven't really seen people using the simplified procedures, and I think it just makes things a little bit more confusing in the code. I do agree though in keeping the envelope procedure and keeping the directional procedure, part 1, because they are vastly different. There was a lot of research that went into one method and a lot of research that went into the other method. One, the envelope procedure is for low-rise buildings. It captures the corners, it gives you economical pressures. And then for buildings that are a little bit taller and different geometry and whatnot, the all heights procedure, directional procedure part 1, is very applicable. One, because the research in the envelope procedure was not done for that, so having those two methods would be great. I think we could drop the other ones. Let me know what you think in the comments below, if you have the same opinion or if you actually use one of the other methods. If you're still here, I have a quick announcement to share. I am actually preparing a course on wind loads, and I'd love to get your feedback. I've realized that there isn't a whole lot of content out there teaching wind loads, so I'd love to cover this in more detail. As I prepare the course, I'd love to get your feedback on my course outline as well as a few questions that I put together. If you're interested in this course, please fill out the survey in the description below. It will take you less than 1 minute and help me out tremendously. Thank you again for tuning in, and I'll see you next time.